Yes, so this is joint work with my two great co-authors who have a much smaller affiliation, actually. So Bruce Minot from Royal Holloway and Olia Romenko from MSR Cambridge. So in the previous talk, we saw what is searchable encryption, what are the goals. So we try to outsource data securely while keeping search functionality. We want to have something that is efficient, but to do so, we have to leak some information. And the point is that this leakage can lead to very, very annoying attacks. And actually, what we try to do in this paper is to reduce this leakage, at least the leakage due to insertions and deletions to the database. To do so, we introduce new definitions to formalize this leakage or this reduction of leakage. And we achieve this definition by using constrained cryptographic primitives. By that, I mean constrained pseudo-random functions and puncturable encryption. And in the end, we also implemented those schemes. Okay, so forward privacy, very quickly, I will not repeat everything what Ki-sung just told you about. So the idea is that you want to have oblivious updates, or at least updates that don't leak any information about the updated keywords. Why do you want that? Because it actually thwarts the devastative versions of the file injection attacks of Zhang, Katz, and Papamanzo. And the annoying thing is that there are not many existing constructions. As explained in the previous talk, we have this first preliminary construction by Stefana Fapantu and Shi, based on ORAM with very expensive updates, or the presentation I presented last year, but that has extremely low update throughput, so that will not really scale in practice. Okay. So again, a very quick detour to what a simple dynamic scheme is in terms of SSE. So usually, index-based schemes suppose that you can map a keyword to the set of results, so to the set dB of W, and you encrypt your database by deriving for each keyword two keys, KW and K prime W. KW will be used to compute some tokens, TI, that will themselves be used as keys in a dictionary in which values will be the masked indices, and the masked will be pseudo-randomly computed using the other key, K prime W, and again, a counter. So to search this encrypted database, the client just sends both of the keys, the subkeys, KW and K prime W, to the server, and it will be able to recompute everything. And to insert a new entry in the database, well, just do as before, as you were encrypting the whole database. Just generate a new token with the new counter value, generate a new mask with a new counter value and the other subkey, and send everything to the server. The problem is that once you've sent KW and K prime W during a previous search query, well, the server will be able to compute future values of TIs. So you will be able to track new insertions for keyword W, and this will break forward privacy. So one question is, can we restrict the evaluation of the PRF that we use to compute the tokens TIs on only a small subset of the counters? And to do so, we're actually going to use constrained PRFs. So remember your Crypto 101 class, you PRF, you just you have a setup or a keygen algorithm that outputs a key, and then you have an evaluation algorithm that outputs the fk of x. With a constrained PRF, you have an additional algorithm called constrain that takes as input the master key and a circuit, and outputs this constraint key KC. And when you run the evaluation on KC and input X, it will actually output fk of x if the circuit, or you can see this as a predicate, evaluates, the circuit C evaluates to 1 on X. And otherwise, it outputs some kind of error symbol. And the key thing is that FK of X is actually looks random as long as you've not issued to the adversary a key that such that the constraint circuit evaluates to 1. So as long as you don't have a valid constraint key, this FK of X is looks random. So this really cool primitive has been introduced concurrently by Bonnet and Waters, Kehas Papadopoulos, Ranopoulos, and Zacharias, and Boyle, Godwasser, and Ivan. And it has many applications, in particular in terms of broadcast encryption. And in our case, we're interested in range constraint PRF, meaning by that the circuit C, the family of circuits we're interested are just circuits that evaluates to 1 when the input is comprised between 1 and n, between two integers. So we call it range circuits. And the idea is that the constraint key for Cn can only be used to evaluate the PRF on this range 1 to n. Once we've got this nice primitive, well, we can very easily build a new forward private scheme. We just do as before for the encryption. We just generate using a counter mode the tokens TIs, the masks, and encrypt using XOR. For the update, again, the client does the same thing as before using subkeys, two subkeys KW and the two subkeys KW and KW prime to encrypt the new entries. And then to run the search, this is the difference. Instead of sending directly KW and K prime W, the server will the client, will actually call the constraint algorithm on these subkeys KW, so that the server can only evaluate the PRF for integers, for counters I between 1 and n. And because the server cannot use K and W to track future updates, you will achieve very easily forward privacy. It's very simple idea, but it actually works, I guess. So we instantiated this generic framework using the tree-based PRF construction from Godreich, Godwasser, and Micali, so we ended up having something that is asymptotically less efficient than Sophos because we have some kind of log factor appearing in the update. But in practice, because we're only using symmetric key operations instead of trapdoor permutations for Sophos, we're actually a lot faster in practice. Diana, this is the name of the scheme, Diana is only IO bounded. I mean, essentially the crypto comes for free. Search is super fast, and update is a lot faster than we got for Sophos, more than 4 times faster. So this is already this is a practical improvement over the previous schemes. Okay, so we saw how to do or support insertions securely and efficiently. What about deletions? We saw, so we can try to answer the question, how could we delete entries in an encrypted database? And essentially in the previous talk, we saw that the answer is usually using some kind of revocation list. For every deleted entry, we add some kind of information to tell the server not to return this entry when we search for a keyword. And this is annoying because the deleted information is still revealed to the server. It's no longer accessible to the client, but it's still revealed to the server. It's kind of not satisfying at all. And this is why the concept of backward privacy had been introduced in the same paper as the forward privacy paper, actually. And the idea is that nothing is leaked about the deleted documents. The server is not able to retrieve some information about the deleted entries. Okay, so what we've done is to actually formally define what backward privacy is. And we gave 3 variants of the definition, from the stronger to the weakest one. So let's quickly take a look. So the backward privacy with insertion pattern leaks the set of documents currently matching the search keyword, which is something that all searchable encryption schemes do. Yeah. It also leaks when they were inserted, and in the end, the total number of updates on the searched keyword W. Then, a slightly weaker version of this definition is backward privacy with update pattern. Here, we not only reveal like the set of currently matching documents when they were inserted, but also when all the updates, both insertions and deletions, happened. So it's slightly more than the previous definition. And then we have the weakest definition of backward privacy, where we leak all of the information that we previously leaked. So set of document matching W, when they were inserted, when the updates happened, but also which update canceled, which deletion update canceled which insertion update. So I will give you a very simple example of the differences between those three definitions. So consider we have this sequence of update. We first inserted a document with two keywords, W1 and W2. Then a second document with keyword W1. Then we removed W1 from the first document, and we inserted a third document containing W2. If we were to search W1 in the backward privacy with insertion pattern, we would leak that the second document matches W, and that this document was inserted during the second update. For the backward privacy with update pattern, we will leak the same as before, plus the fact that this keyword W1 was updated at time for during the first, second, and third updates. And finally, for the weak version of backward privacy, we will leak all of the above, plus the fact that the entry that was inserted at time 1 was deleted during the third update. So we have three different flavors of definitions, and so the question now is how can we achieve these definitions? So let's start with a very basic construction. So the idea is that you actually use again some kind of revocation list, except that the decryption of the entries is done by the client. So during a search query, the client will fetch the encrypted list for documents for entries matching W inserted and matching entries matching W that were deleted. And so it will fetch all these lists, locally decrypt them, and make the difference between those two lists. And those encrypted lists can be implemented using regular forward private SEC schemes. And the annoying thing is that it will require two interactions at least, because you will need one interaction to get documents, and then another interaction, get the document indices, and then another interaction to actually get the actual documents. And the communication complexity is linear in the number of insertions instead of being linear in the number of results. So if you have many insertions, many deletions, and in the end, a very small number of results, well, you're going to pay a lot for this property. So we have two instantiations of this baseline scheme, one based on oblivious RAM, the other one based on regular, more efficient forward private SEC scheme. So we have different trade-offs in terms of security and performance. But the main construction, I think, the main interest of our paper is our last construction is, it's how to build a backward private scheme with optimal updates and optimal communication. And to do so, we have to answer the question, how can we prevent the server from decrypting some of the entries that we've inserted and then deleted? And to do so, we're going to use a very nice primitive called Puncturable Encryption that was introduced by Matthew Green and Jan Myers in 2015 for message encryption, actually. And the idea is that you will be able to revoke some decryption capabilities for some specific messages. So in practice, you're going to encrypt a message along with a tag, and you will revoke the ability to decrypt with a secret key a set of tags. And so the revocation algorithm is called the puncture algorithm. So in some sense, you're going to make a hole in the key so that you're not able to decrypt these tags anymore. And this primitive is based on non-monotonic attribute-based encryption by Ostrowski, Tsai, and Waters. Okay, so how do we do this? Well, very simply, when we want to insert a new entry on keyword W and index end, we just encrypt this entry with the tag, just the tag computing using a hash function on W and the index. And then we add this ciphertext to some possibly forward private searchable encryption sigma. Then, to delete this entry, we just puncture this decryption key on the tag, on the same tag that we encrypted the ciphertext, the entry with. So this can be computed really easily. And then when we do the search algorithm, we just run the search algorithm for the underlying scheme sigma and give the puncture secret key to the server. And the server will then decrypt the non-deleted result, but only the non-deleted result. It will not be able to access to the ciphertext on which the key has been punctured. So again, no access to the deleted results. Okay. One issue though is that the punctured key grows linearly with the number of deletions. And this is a problem with when you have obviously a lot of deletions. The client cannot store everything. So again, the idea is to outsource this storage on the server and to put some elements of the secret key on a new SSE instance stored on the server. And to do so, we need a nice property of the puncturable encryption scheme, namely that the puncture algorithm is incremental. So usually, the secret key of a puncturable encryption scheme can be written as a sequence of constant size subkeys, or at least of size linear in the security parameter. And so you have the first element SK0, that is the first element at the very beginning of the encryption scheme, and all the other elements are generated, or one element at a time, every time you call the puncture algorithm. And so when you call the puncture algorithm, and this is the case for the Green and Meyer schemes, what you actually do is you actually call only a function only of the first key element of the puncture tag and the number of deletions. And this algorithm outputs an updated SK0, so SK0 prime, and a new key element SKD for the new deletions. And well, the only thing you have to do is to store SK0 locally. So now you have only constant size storage, count storage. And I mean, for every keyword, there is a different secret key. So you have per keyword a single element to store. And all the other SKIs are stored on the server and can be retrieved during search by just running the search algorithm on this specific instance of the SCC scheme. All right. So we call this scheme Janus for backward and forward private scheme. So yeah, two-faced God, I guess. So yeah, what's good is that it's both forward and backward private. It has optimal update complexity because we only have to run the puncture algorithm once, and the complexity of this algorithm is actually constant. Again, if we use a constant an SCC scheme with constant updates, constant time update, everything is constant on the side of updates. It has also optimal communication, so constant size communication. But what's not so good is that we have to store one key element per keyword. and per distinct keyword. So if you have many keywords, you will have to store all these elements. But this is actually unavoidable. There is a lower bound on that. What's more annoying in some sense is that the search complexity is actually bad, because for every matching entry, for every result, you will have to decrypt using the decryption, the puncturable decryption algorithm, and this algorithm runs in times linear in the number of deletions. So for every matching result, you have to run an algorithm that is linear in the number of deletions for this specific keyword. So in the end, you have quite large search complexity. And also the P schemes use pairings, and this is not known to be very fast. Okay, so to conclude, yeah, so leakage during updates is a real security issue. So to avoid this problem, we use these nice forward and backward privacy properties. In the paper we presented new way a new framework to construct forward private schemes from constraint PRFs, and a very efficient instantiation. Then also we formally defined what backward privacy is, and we gave some constructions offering different trade-offs in terms of security and efficiency. And in particular, we have this last construction, Janus, which is the first single round-trip backward private construction, and it's based on what I believe is a very, very cool cryptographic tool that might be used in many other settings. Yeah, and so you can find the paper on ePrint, and the code is open source, so you're welcome to take a look. And if you have any question, I'll be happy to answer.
So I guess I didn't follow. What's leaked to the server from the deletions and the growing number of keys, puncture keys?
Sorry?
What's leaked to this? What does the server learn from deletions? And the security definition should capture that, right?
Yeah. So for the last constructions, during an update, you essentially leak the size of the deleted or inserted document, and that's it. Then during the search query,
the size of the document.
Sorry.
I didn't get it. This you leak.
So during an update, so in the formalism I use in the presentation, I suppose that you're only inserting atomic elements, so keyword document pairs. So if you want to insert a complete document, you will have to insert every keyword document pair defined by this specific document. So essentially, you have to run the algorithm, the protocol for every entry.
And the deletions.
And deletions is the same thing. So the adversary is going to learn if you're inserting or deleting a document, but that's pretty much it. And then it will learn more during searches. During searches.
No, that I understood.
Yeah.
So that's capturing the security definition.
Yes.
Hi. So first of all, great work. And one small question is, so in the baseline where you fetch all data, right? So
yes.
You would fetch documents in any way, right, as a search result. So what it matters is round trip of the specific part of data structure to be fetched, right? So
yes.
So in that case, algorithmically, the Janus is extremely interesting, as you said. But in practice, do you think just fetching back documents would be more efficient instead of performing puncturable encryption type of scheme?
You're completely right. Yep.
Okay, but algorithmically, definitely Janus is much more interesting than fetching things back.
Yes, so I'm not saying that Janus is actually something that might be used in practice if you have more than a few deletions, because like the decryption algorithm is very bad in terms of practical efficiency. Essentially, for every decryption, you'll spend 1 millisecond or 1.5 millisecond per deleted entry. So in the end, if you have more than 20 deleted entry for this particular keyword, then you will spend 25 milliseconds for decryption, which does not scale at all.
Okay. Thank you.
You're welcome. It's not. It's not. It's constant time or linear it's linear in the security parameter and in the number of tags. But here we're only using a single tag, so it's constant. It's based on pairings. Yep. So the question was, do I have to use public key operations or strictly speaking, yes, but things can be optimized because essentially the client who owns the secret key is the one who encrypts things. So in the implementation, I actually use the fact that the client has access to all those parameters and so on. That'd be great if we could devise some kind of puncturable secret key schemes that will directly apply to this setting here. Yep.
Okay, I will ask my question as well, and I will use the mic. So, so the fact that you are proportional to the number of deleted documents, this is because of the properties of the puncturable encryption?
Yes.
So there is nothing to do more efficiently if you are in an interval, like consecutive documents, like if you
maybe I'm not sure. Maybe this is so we really wanted to focus on the fact that we're able to delete individual entries instead of being able to delete entire documents as a whole, which covers in some sense more use cases, but is not necessarily super realistic because if you look at the puncture algorithm, somehow we need to have access to the content of the document to delete it. We have to recompute all the tags, and these tags are computed using the index and the keyword. So that was one of the remark of the reviewers actually.
Okay,
yeah.
sounds good. Any other questions?